Electrolysis is just the opposite of of the voltaic cell. Electrolysis is the process by which you're pumping in energy to get the electron transfer to occur. In a voltaic cell, it spontaneously happens because it's going from a high state to a lower state. In electrolysis, you're actually pumping up the electron, so you need an external force. So the electrochemical force, if you write out the reaction, is going to be negative. And the negative electrochemical potential is the minimum amount of energy that you need to drive that reaction. So let's take a look at this. Okay. So here's the two cells, and you can see that on the left is the voltaic cell, and you should be accustomed to it. The anode's on the left, right here. Oops. Actually, I got the wrong. Do this real quick. I don't know why my iPad's not showing up. Desktop, PowerPoint, desktop 2. Okay, let me get out of here. I don't think I'm quite set up yet for do this real quick. I gotta change views, and I didn't hook up my iPad to my computer, so let me go ahead and do that. Okay, here we go. Okay. Okay, here we go. So what you will see on the left here is the voltaic cell, and you notice that the anode is the left part of this cell, the cathode is the right part of this cell. This is a spontaneous reaction, so delta G is negative, and the electrochemical potential E0 or E is positive. And the electron is going to get pumped from the anode to the cathode. You get the oxidation at the anode, you get the reduction at the cathode. In an electrolytic cell, the main difference is that delta G is positive, electrochemical potential is negative. So therefore you need a power supply, an electron pump, to take the electrons from the anode and push it into the cathode. Because you have an electron pump, okay, that means that the battery has to attract the electrons and then push the electrons. So what's going on here is that the battery is going to be positive at this end, negative at this end. It's going to pull the electrons here and pump the electrons there. But notice that the anode is still the positive terminal, and the cathode, sorry, the anode is now the positive terminal, and the cathode is the negative terminal. That's the main difference between the two cells, is that the sign of the electrodes are opposite. In the voltaic cell, the anode is negative, the cathode is positive. In an electrolytic cell, the anode is negative and the cathode is positive. Okay, that's one of the main difference. The other main difference, here it is right here, is that delta G is positive for the electrolytic cell and delta G is negative for a voltaic cell. So let's take a look at this real quick. What we have is an electron pump, And just check real quick. I actually had this backwards. I apologize for that. This was backwards. The electrons here are being attracted to the positive terminal of the battery, and then they're being repelled by the negative terminal of the battery. But the battery is the electron pump. Okay, so that's what you see in this diagram right here. You have a battery, and for those of you who've taken electricity, you designate a battery by two parallel lines, and one is longer than the other. The longer portion is the positive terminal, the shorter uh, line is the negative terminal. So here I show you an ever-ready battery, and this is how the schematics are. The electrons are being attracted by the positive terminal. Remember that the anode now is the positive, and then it's being repelled by the negative terminal. Remember now that the cathode is the negative terminal. So that's electrolysis for you. And why is electrolysis important? Because, believe it or not, that's how you got your utensil coated with a certain element that may resist corrosion. So again, these are a summary of the electrolytic cell. Two electrodes, inert or non-inert. If it's non-inert, then basically you're coating the that electrode with some sort of chemical. An external power source, drive a non-spontaneous reaction. So that basically is the key essential of an electrolysis. Now let's take a look at this right here. This would be a typical electrolysis cell. Suppose we have molten sodium chloride. So we take sodium chloride, pure, solid, and we heat it up so that it becomes the molten state. It's kind of like a liquid state. Okay. What we can do now is we can put two electrodes in there and see what the reactions will be based on the chemistry that occurs. There's a question here: if the electrons are being repelled by the negative side, should the arrow be going the other way? Let me go back real quick and clear this. So remember that we are driving a non-spontaneous reaction, but we still need electrons to flow. So if we have a positive terminal here, the electrons are going to be attracted to the positive terminal. And then what's going on is that the negative terminal is going to, remember, like charges are going to repel each other. So that means that the electrons are going to be pushed away. So that's what's going on here. So we have an arrow. This is only a one-way street. We can't have the electrons coming in one direction and electrons leaving in the same direction. It's going to be moving in the opposite direction. Okay, so that's what's going on with that battery. Anyway, if you take a look at what we have here, the way you analyze an electrolysis is you always identify the ingredients that you have. Okay, so the ingredients here are sodium chloride and the electrodes. The electrodes could be like a carbon graphite or platinum wire, something that's not going to undergo electrolysis, because we can't actually have sodium metal as an electrode, and certainly we can't have chlorine as an electrode. So what we have is maybe the electrode could be like a carbon graphite. So in this particular case, I put a platinum inert. So these are the key ingredients in this electrolysis cell. Then you have to look at the species, and the species are going to be the platinum, metal, the sodium ion, and the chloride ion. And how do you know it's a sodium ion and chloride ion? Because you got sodium chloride. So the sodium chloride is a sodium cation and the chloride anion. It's not sodium solid and chloride gas. In sodium chloride, you've got the ions. And then you have to determine, this is where you have to think about the chemistry that is going to occur. There's going to be an oxidation and there's going to be a reduction. The oxidation always happens at the anode, the reduction always happens at the cathode. Okay, so that's the thing that you have to remember. You have to have two columns there, one for the anode, the oxidation, one's at the cathode, the reduction. So you take a look at your species, sodium and chloride. Don't worry about platinum, it's an inert, so that's not going to do any type of chemistry. But if you take a sodium cation, what is its likely chemistry? Do you think the sodium cation will go to +2, or do you think it'll go to 0? Well, your chemistry sense tells you that there's no such thing as a sodium +2. If you had a sodium +2, you would be breaking the noble gas electron configuration when it's sodium positive. So that's not going to happen. Most likely, what's going to happen is that it's going to gain an electron and become sodium neutral. Okay, so by gaining an electron, now it becomes sodium neutral. It goes from positive to 0. That's actually a reduction. So you would put sodium in this column right here. Look at chlorine, Cl minus. Cl minus is not going to go to Cl minus 2. It's not going to undergo further reduction. Most likely, chlorine minus will go to chlorine gas, chlorine 0. So Cl minus to Cl 0 is an oxidation. So that's what you want to put here. You want to say that Cl minus goes to Cl2, and as a Cl2, it's a 0 oxidation state. You got to put the 2 electrons here, and you notice that 2 electrons on the product means that you are losing electrons. That's an oxidation, which is the correct column for the anode. The other chemical is going to be sodium. You know that sodium is undergoing reduction to sodium 0, and you're going to need an electron on the reactant side. So those are the likely event that is going to happen at the cathode, which is that, and the anode, which is that. All we've got to do now is figure out how much energy do we need to drive these reactions. And so you look these up in the standard reduction potential table. And when you do that, okay, when you do that, you get this. Okay. Let me just clear this up for you so that you guys can see what I wrote here. Okay. The chlorine is undergoing oxidation. The sodium is undergoing reduction. We look up the electrochemical cell. If you look it up in the back of the book, you're going to see negative 2.71 for the reduction of sodium. For the reduction of chlorine, you're going to see positive 1.36, but because now we write it as an oxidation, we change the sign to minus 1.36. Okay, so these are the electrochemical potential, and since these are the only two reactions that are going to be at the anode and the cathode, then we can certainly say that chlorine minus plus sodium plus is going to go to Na solid plus Cl2 gas. That's the net reaction. Na solid plus Cl2 gas. And then we have to balance it that way. And in order to do this correctly, you notice that we probably need 2 sodiums here and 2 sodiums there, just so that the charge on the left is net zero. But, and then what exactly is going to be the cost to drive this reaction? All we have to do is add these two, because one's an oxidation, one's a reduction. That comes out to minus 4.07 volts. So to do this electrolysis and actually plate out sodium solid and generate chlorine gas, we need a battery of 4.07 volts. And if we can do that, then we can get this reaction to occur. So this is just a very simplistic analysis of how you figure out an electrolysis problem. Let's go to something more complicated. Well, before I do that, let me just show you the electrolysis of water. And the reason why we need to do the electrolysis of water is because, remember what I said about Chem 201? You're generally dealing with aqueous solution, and so water is going to be part of the ingredient. And so before we move on and do these other examples, I have to show you what the chemistry is when we oxidize and reduce H2O. So in this particular diagram, what we have is electrodes, and that could be platinum wire as well, and water. And water is going to be not so much our ions, but it's the species that is going to undergo chemistry, because water is not an ion, but it will undergo oxidation and reduction. And if you look it up, the oxidation of water is going to be generating oxygen gas. Okay, H2O will go to O2 gas. And that's because the oxidation state of oxygen in water is a -2, but the oxidation state of oxygen in gas is 0. So that's an increase in the oxidation state. That's an oxidation. So this reaction down here in the anode is the oxidation of water. And then this reaction over here at the cathode will be the reduction of water. So what you guys need to write down in a good sheet is these two reactions right here. Here you can see that the water is undergoing oxidation. The species, the element that is undergoing oxidation is oxygen. It's going from -2 to 0. The hydrogen is still +1 in both sides. So that's not undergoing any type of reaction. So that's the oxidation state at the anode. At the cathode, what you have is the reduction of hydrogen. Here it's +1, but in hydrogen gas it's 0. So it's going from a +1 to 0. That's a reduce, that's a lowering of the oxidation state. That's a reduction. Notice that the oxygen here is -2. The oxygen here is also -2. So oxygen doesn't do any type of chemistry in the cathode. It's the hydrogen that does that. But what's important is not is the chemistry as well as the electrochemical potential. The reduction of water is going to cost you minus 0.83 volts. Okay, you can find that in the standard reduction potential. It's going to cost you minus 0.83 volts. In other words, you need a minimum of 0.83 volts just to reduce water. But remember, it's got to be coupled. And the oxidation of water is going to cost you minus 1.23 volts. And so when you're actually, and you've probably done this a bunch of times, I know I do it as an easy demonstration. I basically take water, I put a little bit of salt in here, and the salt just acts to make sure that there's a conduction process that goes on. And then I just drop a 9-volt battery in here. And what happens is that the 9-volt battery has enough voltage to cause the electrolysis of water, and what you get is bubbles that are occurring in the terminals. And one terminal is going to have twice as much bubble as the other one. And when we do the stoichiometry, you could probably guess what what gas that particular terminal is, and therefore you can figure out what the anode and the cathode is. But this is the net reaction when you do electrolysis of water. Water breaks down to hydrogen gas right here and oxygen gas right here. The H plus and the OH minus, well, they tend to cancel out, but the electrolysis of water is going to generate hydrogen and oxygen. And it's going to cost 2.06 volts. Okay. That's how much energy you need theoretically to split water. And it doesn't seem like that's a very high enough power to do this. And you could do it with a 9-volt battery, which is overkill. But it's costing you more energy to split water than the energy you get out from the hydrogen fuel. That's why it's not practical. That's why we don't try and generate hydrogen this way, because it's a losing deal. What you want to do is you want to generate hydrogen through something that is more economical, like the sun. But that's for another story. Anyway, remember these two reactions because we're going to see them again as we talk about more complicated electrolysis problem. So let's go to this particular diagram. Now we have seawater, and seawater, as you know, has sodium chloride and water. So if we want to know what is the net reaction that takes place if we put two electrodes and then we use an electron pump or a battery to drive the reaction, what is the likely reaction? And the likely reaction will always be the reaction that costs the least amount of energy, the one that is going to be the path of least resistance. So in order to do that, you guys have to do the analysis. You have to break down the species, the ions or the chemical that is going to undergo chemistry, the anode, the cathode, and then this right here needs to be over here. So when we do that, okay, this is, again, I'm just diagramming the different parts of the electrolytic cell. This is called an electrolytic cell. Whereas a battery is called a voltaic cell or a galvanic cell. Electrolysis is called electrolytic cell because you need to drive that reaction that is not spontaneous. So here I'm showing you the anode, the source of the electron, and then I'm showing you the cathode, and then the positive terminal and the negative terminal, and then the half reactions that will occur. Okay, and the half reactions are going to be down here, not so much here, okay, because we now have water as a X factor. We got to put that in. So let's take a look at this. These are our ingredients. We have platinum, sodium chloride, water. The ions or chemicals are sodium ions, chloride ions, water, and water. At the anode, we know from our previous example, it's the chlorine that's going to undergo oxidation, and then one of these waters is going to undergo oxidation. At the cathode, we know that the sodium is going to undergo reduction, and then water is also going to undergo reduction. So if we do this, this is the breakdown. Notice that the chlorine is undergoing reduction, and then water is undergoing reduction as well. And then at the sorry, oxidation. I meant oxidation. And then at the cathode, the sodium is undergoing um, oxidate reduction. Reduction to going from plus to zero, and then water is also undergoing reduction. And so we put the electrochemical potential, and what we need to do is we need to figure out what are going to be in competition with each other. I apologize for the format. This should be under this column, and this should be under this column, okay? Because this is the oxidation potential. This should be the reduction potential for water, okay? The formatting got messed up, and those two should be switched. So what we need to do is we need to look at the two competitions at the anode. These two chemicals, change gears, are going to be at the anode. Both will undergo oxidation, but the one that is going to undergo oxidation is the one that is um, requires the least amount of energy. So is 1.36 lower or 1.23? Um, and not so much lower in the sense that it's more negative, but um, more spontaneous. Remember that we want electrochemical potential to be positive because that's the more spontaneous process. So between these two process right here, the chlorine and the water wins out because that's going to be the more likely event. That's the least negative, which means that it's going to be requiring the um, less amount of energy to drive. Then we also do the same thing with the cathode. And in the cathode, it's this competing with this right here. And we're looking at the potential to see which one again is the least negative, more positive. And that's the one that's going to be the one that will require the least amount of energy. You can see that minus 2.71, minus 0.83, minus 0.83 wins. So if you're trying to take salt water and you're trying to get sodium metal out of it or chlorine gas out of it, what you end up doing is splitting water. Okay, what you end up doing is doing neither, because the water will go in there and split before you can furnish enough energy to get the sodium and the chloride to undergo chemistry. Okay, and it is the path of least resistance. That would be the chemistry that occurs. Let's take a look at another example. Okay, here is the electrolysis again of sodium chloride. I think, let me just see real quick if this is the same. Apologize for that. Yeah, this one's messed up. Let me go to a different electrolysis source. Um, let's go to this problem right here, magnesium chloride. And what I want to do now is, because the formatting is really messed up, I'm going to go to my computer so that you guys can see this in a better light. Okay, so that the transitions are smoother. So let's take a look at this problem right here. In this particular case, we have magnesium chloride in aqueous solution. Again, remember what I told you. You have to break up what the components are. And the components are magnesium chloride and water. So that's what we need to identify. Magnesium chloride and water. What are the chemical species that will undergo chemistry here? Well, um, there's a question. You got to make sure that the number of electrons on both sides are going to be the same. Remember that you have to flip when you get this, when you're doing that reaction. Uh, no, one's an oxidation, one's a reduction. Lee, all you've got to do is add both of them because the electrons are in opposite side. So you just add it. You don't have to flip one, and the waters will not cancel. Okay, the waters will not cancel. So, um, so take a look at this that I have on your screen. This particular um, electrolysis has magnesium chloride and water. So the species are magnesium ions, chloride ions, water, and water. At the anode, the chlorine is going to undergo reduction. I mean, the chlorine's going to undergo oxidation. Remember, anodes always oxidation. And one of the waters will undergo oxidation. So that's what we have. We know that the chlorine is negative 1.36 volts and water is negative 1.23. Between those two, water is going to be the favorable reaction. The cathode, we have magnesium, that's a new chemical that we haven't seen before, and water. We know that for this water, it's negative 0.83, but the magnesium is negative 0.237. So that's the value you will find in the standard reduction potential. Again, what you are doing is looking at the competition, and the competition here is between this and this. And the way you figure out which of these two chemical is the winner is by looking at their driving force. One will require 1.36 volts, the other will require 1.23 volts. The water is going to be the one that's going to be driven. And then these two at the cathodes are going to be competing. But one requires 2.36 volts, the other requires only 0.83 volts. So again, in this particular electrolysis, you do not get the desired reaction that you're aiming for. That is, you do not do any chemistry with the magnesium or chlorine. You end up doing chemistry with water. Okay, the anode is going to be the oxidation of oxygen. The cathode is going to be the reduction of hydrogen. When you add those two up, what you will end up with is you will get the water going to oxygen and hydrogen. Remember that when you have an H plus and an OH minus, you end up with water in that reaction. That's why they tend to cancel. So that reaction really did not get us anywhere. It's the same as the sodium chloride. Okay, so that's why you always have to be weary of water because it can cause side reactions. Here's an example where we use iron nails. It's a non-inert electrode. Inert means that it's not going to react with anything. When I say non-inert, it means that it will react with something. So let me just go through this real quick. This one is going to be sodium chloride, seawater, and iron nails. So what are the species? Iron, sodium chloride, and water. So in this particular case, what we will see is that at the anode now, we will see the oxidation of iron because that's a likely chemical reaction. Iron is not inert, it will undergo oxidation, and it undergoes oxidation of positive 0.44 volts. That's actually a spontaneous reaction. You don't need energy to drive that reaction. Then we also see that sodium will undergo reduction. We've already seen that reaction. The chlorine will undergo oxidation. We've already seen that reaction. And then, of course, both waters will undergo reaction. So now, again, we played this game as to these are the chemicals that will most likely be occurring at the anode, the iron, the chlorine, and the water. And we look at the electrochemical potentials, and we see that the iron is going to be the one that is the most favorable to drive. In fact, you don't need energy to drive that reaction, but it has to couple with a reduction. So we have to figure out which between these two are the likely reaction at the cathode. And you'll see again that water here is going to be the likely reaction because it's going to require the less amount of energy. So when we add those two up, that's the reaction that occurs at the anode, that's the reaction that occurs at the cathode, that's the oxidation, that's a reduction, and we get a net voltage when we add those two of minus 0.39 volts. That's the energy that you need in order to drive this reaction. And so what happens is that at the anode over here, you actually get the rusting of iron from iron 0 to iron plus 2, and then at the cathode you still generate a whole lot of hydrogen. So you can see if you do this systematically, it's not a difficult problem to solve. I'll do one more. I'll skip this one because this one has a net electrochemical reaction of 0. I'll do this one, electroplating. This is an example of nickel electroplating. We're going to plate these electrodes with nickel, and we'll see if we can do that, whether and how much energy do we need. So again, the species are nickel ions because that's what's in my solution, and water. And so nickel bromide will undergo reduction to 0. Bromine will undergo oxidation to Br2. Water will undergo reduction. Water will undergo oxidation. If you look up the electrochemical potential for nickel, it's minus 0.28 volts to reduce it. To oxidize bromine, it's minus 1.065 volts. Again, we have to look at the competition between bromine and water. You will see that minus 1.065 volts is going to be the path of least resistance at the anode. At the cathode, we're looking at these two, and you can see that negative 0.28 is more is going to be the path of least resistance. It's going to require less energy than negative 1.23. So indeed, when you do this reaction, what happens is that you do get the oxidation and reduction of bromine. You actually do get this reaction right here. And what is the total potential? The total potential would be minus 1.065 plus or minus 0.28. So that's the amount of energy that you would need to drive this reaction. So in the end, you end up with 1.345 volts to do the electrolysis or the plating out of nickel on, say, if you want to electroplate a metal with nickel, then you use that metal as an electrode, and then the nickel will adhere to that metal. That's how electrolysis is done. So moving right along, I told you a lot about the chemistry of water, and that water requires 2.06 volts to take place. In actuality, it actually requires more than that. And the reason why is because we need to put in more energy than the theoretical minimum because of kinetic barriers and other um, forces we have to overcome. And these other forces are called the overvoltage. Okay, the overvoltage is the extra energy you need to supply to get it through over the activation barrier so that the reaction does occur. And again, it's because of slow electron transfer and the kinetic process. And generally for water, you need to add an extra zero point 0.4 volts to the total. So it's not a spontaneous thing. Um, Changing gears real quick, here's a typical example. You guys will see this in your activity for lab next week. Uh, a solution contains hydrogen ions, copper ions, calcium ions, nickel ions, each at a concentration of 1 molar. So they are at their standard state. Determine the sequence of ions to be reduced at the cathode. So reduction means that their charge goes down or lowered. So hydrogen will be going to H2, copper plus 2 goes to copper metal, calcium plus 2 goes to calcium metal, and nickel plus 2 goes to nickel. What you need to do is you need to look up the electrochemical potential for these and then figure out, based on the electrical chemical potential, which one is going to be the most spontaneous, followed by the one that is going to be the requires the less energy to drive. So just going based on these potential, I know that this is the most positive, so this is number one. This will be the first. Then this would be the second. Hydrogen would be the third, and then finally calcium would be the fourth. So that would be the sequence by which these ions are going to be reduced at the cathode. Okay. And in fact, if you have water in your electrolysis, the calcium will never get reduced because the water will go in there and be reduced first before the calcium. But basically, this is the sequence. The copper first, the nickel next, followed by hydrogen, and then the calcium if you don't have water. Otherwise, water will go in there and get reduced, and then you may not ever get to calcium. Okay, here's an example that I wanted to show you. Remember, I showed you a similar example like this in the ACS practice test. And it looks like this type of question is a question that we've never covered in class. And so why are we discussing it when we haven't even covered it yet? And that's because I want to show you the magic of dimensional analysis, okay? And the magic of dimensional analysis means that you don't even have to worry about deriving the equation. You just let the units work it out for you. So let me do this real quick. Right here. There's a couple of things that you need to know. An ampere, which is a unit of electricity, is an amp, that is current, is a coulomb. 1 amp is a coulomb per second. And then a Faraday is a coulomb per mole of electrons. 96,500 or 96,485. So take a look at this problem. Silver is electroplated. What mass of silver plates out if 6.8 amps flows through the cell in 72 minutes? Okay, so we're looking at the mass of silver that is going to be produced by this electrolysis process. So let me show you what how you would approach a problem like this, just using plain dimensional analysis. We have 72 minutes, and we know we need seconds because that's the unit of amperes. So change 72 minutes to seconds so that you can do dimensional analysis. For every 1 minute, there are 60 seconds. So 72 minutes is going to be approximately, or is equal to, take my calculator out, 432 seconds. Okay. Yeah, 432 seconds. Actually, 4,320 seconds. I'm off by a factor of 10. So let's solve this problem using dimensional analysis. We know that we have 6.8 amps, and that's coulombs per second. That's the problem that we have here, okay? And we're going to be doing the electrolysis for 4,320 seconds. So the seconds cancel. We know that there are 96,485 coulombs in 1 mole of electron. So the coulombs cancel. And we also know that for this reaction right here, it takes 1 mole of electrons to reduce 1 silver. And then finally, if you look up the atomic weight of silver, you will see that silver has an atomic weight of 107.87. So you can see what I did. I didn't use any equation that I memorized. I just let the units work it out for me. I use the fact that an amp is a coulomb seconds, so I got rid of seconds by multiplying by the time. Then I use the fact that a Faraday is coulombs per mole, so I use that and divide it by that quantity so that my coulombs can cancel out. Then I use the balance equation to realize that for every 1 mole of electrons, I can reduce 1 mole of silver to silver metal. So that's basically this conversion factor. And finally, I use the molar mass of silver to show that for every 1 mole of silver, I get 107.87 grams. So this is a problem where dimensional analysis really plays a key role, because otherwise you're going to get stuck. You're going to figure out, now how do I convert amperes to something else to get mass? And you're going to get stuck because we didn't derive that equation, but through dimensional analysis. And that's why I always stress dimensional analysis. The equation comes out, the equation reveals itself. Because this reaction is a reduction, you notice it's going from Ag plus to Ag0. It's a reduction, and reduction happens at the cathode. So that's the answer for this. What electrode will the silver played out on? The electrode will be the cathode electrode. So let me just show you the solutions here. Let me clear my slate here, and you can see exactly what's going on. I do the dimensional analysis. I convert minutes to seconds. I use 6.8 coulombs per 1 second. That's 6.8 amps. I use Faraday's constant. I use 1 mole of electrons for 1 mole of silver, and I use the atomic weight of silver, and I get 32.84 grams of silver will played out if I carry out this electrolysis in 72 minutes. Okay, so here's another problem. Copper can be electroplated at the cathode of an electrolysis cell by the half reaction. How much time would it take to plate out 325 milligrams of copper? Again, you want to use 0.325 grams of copper. use the atomic weight of copper to get it to moles of electrons. And the atomic weight of copper happens to be, let me find that in my periodic table. I'm just going to set this up for you, and then you guys can see again how dimensional analysis works. I got 63.55 grams per 1 mole of copper. From this reaction, I can say that 1 mole of copper actually is equal to 2 moles of electron. See this right here? That's where I got that ratio. That's why you need a bit to make sure that your equation is balanced. Now that I have my moles of electrons, I can use Faraday's constant, 96,485 coulombs is 1 mole of electrons. I can use the amperes, 5.6, remember it's 5.6 coulombs per second. That's an amp. So 5.6 coulombs per second. That's my amp. And if I cancel that, cancel that, cancel that, and cancel that, I'll get my time. It's amazing what you can do with dimensional analysis. You just set up the units and it'll come up to the correct answer. And that's what you see right here. Okay, that's what you see right here. Let me clear my slate. I use the mass, I use the molar mass, I use the mole ratio, I use Faraday's constant, and I use the amps, just like I did. And when you carry out the math, it comes out to about 176 seconds because I only have 2 significant figures in my amps. Then I round it off to 180 seconds. So that is electrolysis for you. And again, these are this is a diagram showing you the difference.